Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to solve one design example for a built-up section and design of lacing. So the statement is design a column of length 8 meter pinned at both ends. So the length is 8 meter, it is pinned at both ends, consists of two channels back to back at a distance 250 millimeters. So it means the channels are back to back and the distance between these two channels is 250 millimeter. Also design flat lacing, mean we need to design the lacing as a flat element with B width and T thickness. And the 15 millimeter diameter rivets are used to connect this lacing with the flanges of the channel section, and the applied factor load is 3200 kilonewton. So the load is 3200 kilonewton and we are given that it is a pinned end, so it means K is equal to 1 and length is equal to 8 meters, so KLU is equal to 8 meters. So it is same in X as well as Y direction. Okay, so to select the section we need the required area, and for that we need to assume the slenderness ratio value. So initially we can assume the slenderness ratio for built up section equal to 70, and corresponding to this we can calculate phi CFCR by comparing this R assumed with RC. If it is less than RC, mean 133 for A36 steel, then we can use the FCR formula 0.658 Fy over Fe times Fy. By using this expression we can calculate phi CFCR. Once we have phi CFCR, then we can calculate the area required, Pu divided by phi CFCR. So it will give us the required area. So this is for double channel. So for single channel section it will be half of it, so divided by 2. Now we need to select the section from the properties table such that it has area. A single channel section has area close to this 9220 millimeter. Its B should be more than B minimum, mean 54 when one leg is connected, and 15 millimeter rivets are used. So from the properties table we can select the section with the area close to this one. So the selected section is 3MC modified channel section 330 by 74, and it has cross sectional area equal to 9480 for single channel section. So it is close to this 9220 value. So we have done this practice many times, how we can select the section from the properties table. So I will directly go to the selection of this table and the properties from the manual, design manual or design aid manual. So from that properties table we can select the properties for this channel section: RX117, RY26.9, D mean depth of the channel section, D 330 millimeter, BF flange width 112 millimeter, thickness of flange 15.5 millimeter, and thickness of web 20 millimeter. So these properties will be used for further calculations. Okay, after selecting the section we need to perform the local stability check for web as well as flange. So for flange it is BF over TF, so BF is 112 and TF is 15.5, so it comes out to be 7.23 and it should be less than lambda R, which is 15.8. So we can use this table and we can select the corresponding value for lambda R, and it is 15.8 for A36 steel. So 7.23 is less than 15.8, it means it's okay. The flange is not a slender section. Flange of the channel section is not a slender section or slender element. So next we need to check for the web. So for web, H over TW should be less than lambda R. And if we see channel section, so we have the total depth. Total depth is D, and the width of this web is equal to H, and this H will be equal to D minus 2 times thickness of flange, thickness of this flange as well as thickness of this flange. So D minus 2 times thickness of flange divided by thickness of web, so it will give us the H over TW, it is 14.95, and the limiting slenderness ratio lambda r for the web is 42.1. Again, we can use this table to select the corresponding value. So this is also satisfied, so it means the local stability check is satisfied for both web as well as flange. So next is to check for the global instability. For the global instability, we need to determine the R value in both direction, X as well as Y direction. So Rx will be same as that of the channel section, but Ry will be changed. So we need to calculate the Ry value. So we can calculate the exact value of Ry by calculating I of the built up section about y-axis as well as the total area. So to calculate the Iy, either we can use the approximate expression that is given in the LRFD design manual, which is equal to 0.6 times b, the distance between the channel webs, or we can use the exact calculation Iy is equal to Iy of built up section is equal to Iy of individual section plus AR square, and R is the distance from the centroid of this channel up to the center of this, or up to the centroid of the built up section. So from here we can calculate the Iy value, and from Iy we can calculate Ry. So once we have Rx and Ry, then we can calculate the slenderness ratio. So slenderness ratio we need as KLx as well as KLy are equal to 8 meter. So we need to select R minimum out of Rx and Ry to calculate the maximum slenderness ratio. So KL over R minimum, and R minimum is 118.8. So it is corresponding to Rx. So Rx is 118.8. So R minimum is 118.8. So corresponding to that, we can calculate the maximum slenderness ratio, and it comes out to be 68, and it is less than 200. So it means globally our section is stable. And one thing we need to recall that in the previous video I have discussed that in case of lacing, the distance between the lacing point is small, so the slenderness ratio of the individual member will be small, and there will not be any chance of buckling in the individual member. So as the slenderness ratio of individual member A over Ri is small, so the modified slenderness ratio will also be close to the original slenderness ratio of the built up section. So in that case, in case of lacing, we need not to calculate the modified slenderness ratio. Okay, based on this slenderness ratio, the governing value are depending on the R minimum. So we need to calculate phi CFCR value, which comes out to be 176. Again, it is corresponding to the formula phi CFCR is equal to phi C times 0.658 times Fy over Fe times Fy. So I have discussed this formula many times. So we can use this expression if there is inelastic buckling to calculate the phi CFCR value, and then based on this phi CFCR we can calculate by multiplying with the area of the section, we can calculate the capacity of the section, and it is 3338 kilonewton, mean 3338 kilonewton, which is more than 3200 kilonewton the applied load. So it means it's okay, our selected section is capable to resist the applied loads. So the final selection is this one, because this section satisfies the local instability, global instability, as well as the strength checks. Okay, after finalizing the section, then we need to design the lacings. So to design the lacing, first we need to calculate the shear force that this lacing must be resisting. So this shear force that this lacing need to be resisted, or this lacing should resist, is given by 2% of the capacity of the section. So 0.02 times the capacity of the section, axial load capacity of the section, which is 3338. So it comes out to be 66.8 kilonewton. So this much shear must be resisted by the lacing elements. Okay, after that we need to calculate the distance between the holes, which is equal to S. So this S is equal to B plus 2G when the angles are connected, channel sections are connected back to back. So the distance between these rivet points is equal to S, and it is equal to the distance between the webs, which is 250, plus the gauge distance on this side as well as the gauge distance in this side. So in case of channel section, we have studied in case of tension member the standard gauge length. So for different channel section, the standard gauge length is given based on the length of the flange or the width of the flange. So if the flange width is more than 100, so in that case gauge length is 64. So for our section the gauge length is 64. So S will become B plus 2G, 250 plus 2 times 64. It is 378 millimeter. Mean the distance between the rivets of the flanges of built-up section will be 378 millimeter. Okay. So after that we need to decide whether we should use single lacing or double lacing. So for that we have a criteria that if S is less than 380 we should go for single lacing, and if it is more than 380 we should go for double lacing, and our value is 378 less than 380, so we will provide single lacing. And in case of single lacing the angle is 60 degree. The angle with the vertical is 60 degree, theta is 60 degree. So this is the configuration. Here this is S starting from this rivet up to this rivet, this is spacing, and this is G. Okay, after that we need to calculate the longitudinal length between the lacing point, mean the distance between these lacing point. So it is equal to 2 times of S cot of theta. So this much distance is S cot of theta, and in case of single lacing we will have double of it, so it will be 2 times S cot of theta. So when we substitute the value of S as well as cot of theta, it comes out to be 437 millimeter. So now we need to check that within this length L, the flange should be safe for the buckling. So for that we have an expression 4.61 L over TF, and it should be less than the slenderness ratio of the it should be less than the governing slenderness ratio of the built-up section. So this factor 4.61 L over TF, it will be 4.61, L is 437 and TF is 15.5. So it comes out to be 130, and which is more than 68. It means if we use a single lacing with angle 60 degree, then this flange will not be safe against the buckling. So we need to revise our angle in such a way that this distance is reduced, this L is reduced. So for that we need to increase this angle theta. So in that case this L will be reduced. So now select a higher value of theta equal to 75 degree. So after, if we substitute the theta 75 degree in this expression, so L will comes out to be 203 millimeter. And if we check this expression 4.61 L over TF, so it comes out to be 60.4, and it is less than this 68 value, the overall slenderness ratio of the section that we have calculated earlier. Here 68. Okay, so it means this check is also satisfied. So we are using single lacing with angle 75 degree. So after that we need to calculate what will be the force, compressive force in this lacing element. So the compressive force in the lacing element is given by Fu, which is Vu divided by N sine of theta, and here N is the number of faces. So one face on this side and the other face on the back side. So N will be 2, Vu is 66.8, we have already calculated, and sine is theta is 75. So Fu comes out to be 34.6 kilonewton. So this is the force in the lacing element. After that we can calculate the length of lacing, mean the length of the lacing element. So it is given by S over sine of theta, effective length of lacing element. So what is effective length of lacing? We have already discussed in the previous video, so you can refer to that video. What is this effective length? So it is equal to S over sine of theta. S is 378 and sine 75, it comes out to be 391 millimeter. Okay, after that we need to select the section for the lacing, and we need to select a flat section, mean it should be a rectangular section with width b and thickness t. To select that section we need to satisfy 4 conditions, mean the slenderness ratio of this lacing element should be less than 140, the area of the required area of the lacing element should be more than fu over 5 CFCR, or the area provided should be less than area required. We also need to satisfy the local buckling criteria, B over T should be less than 10.8. We also need to satisfy the minimum width for the connection or to provide the rivets, which is B should be greater than 3 times diameter of the rivet. So we need to satisfy these 4 conditions for the lacing element. So we can decide the dimension B and T of the lacing element in different ways. Either we can assume one value and then calculate required area of the lacing element based on the maximum slenderness ratio 140 and calculate 5 CFCR, calculate required area, and then calculate B value, and then apply the check local stability and global instability as well as the strength check. So 2 approaches can be adopted. So first I will show this approach that I have presented in these slides, then I will again discuss the second approach that can be used. Okay, if we see the properties of this flat bar, so area is equal to B into T and I minimum is equal to BT cube over 12. Or I is equal to BT cube over 12. So R minimum will be equal to BT cube over 12 divided by BT, mean area, so it comes out to be 0.289 T. So once we have R minimum, we also have effective length LE, so we can calculate the slenderness ratio LE over R. So it should be less than 140. So we know the LE value and we know this R, but it is in the form of T. So when we substitute these values, so here it should be 391 divided by 0.289 T less than 140. So it comes out, T comes out to be 9.02. It means T should be more than this value. So we can select the higher value of T from this 9.02. We can select 9.5 or 10 millimeters. So let's suppose we select it equal to 10 millimeter. So now we have one dimension T. It should be equal to 10 millimeter. Then we need to select the B. Okay, to select the B, we can calculate the required area. So for that we need this 5 CFCR, and for 5 CFCR we need the slenderness ratio. So now we can calculate the slenderness ratio LE over R, because we have this LE 391 and we have this R value 0.289 times thickness of the plate, because we have already calculated R minimum is equal to 0.289 T. So 0.289 thickness 10 millimeter. So this comes out to be 126.3. So this value may be a little bit different because we have incorrectly written 365 over here. It should be actually 391. So we can calculate the exact value. What is the exact value of this LE over R? So for example, the LE over R value is 126.3. So corresponding to this slenderness ratio, we can calculate the 5 CFCR by comparing it with RC and calculating the using the corresponding formula of 5 CFCR or FCR. Okay, so once we have the 5 CFCR value, we can calculate the required area, which is FU, the load or the force in the lacing element, divided by 5 CFCR. So required area will be given by this equation, and this should be equal to B times T, and we know the value of T, which is 10, and B is unknown. So we can write this required area in term of B into T, and T is 10, so B into 10 should be equal to PU over 5 CFCR. So from here we can calculate B value. So B should be more than 36.2 millimeter. So from this criteria, that area selected should be more than area required. So we can find out the value of B, and we can term it as a B minimum, or we can say B should be more than this value. Okay, so now we have T is equal to 10 millimeter and B is equal to 36.2 millimeter. So now for the next proceeding, either we can just check B over T and it should be less than 10.8, or we can again find out the value of B corresponding to this criteria. So if we find the value of B corresponding to this criteria, so it will be B should be less than, because B over T should be less than 10.8. So B should be less than 10.8 times 10. So it is 108. So B should be less than 108, but it should be greater than 36.2. So this is from the third criteria. So next, the fourth criteria, that B should be greater than 3D. So from here again we can calculate the minimum value of B. So for that, if we see, the B should be greater than 3D, so 3 times diameter of rivet 15, so it is 45. So it means the minimum value of B should be 45 and the maximum value should be this one, 108. So we can select a suitable value in between these two, 45 and 108. So let's say the B is 50 millimeter. So now we will have the section 50 by 10. B is 50 and T is 10. So if we check all the four limitations, mean LE over R, B over T, and B should be greater than 3D, and phi CPN, if we check these four limitations based on this selected section, so these four limitations should be satisfied. So this is the one way to proportion the section for the lacing element. The second approach is, first we, based on the first condition that LE over R should be less than 140, so consider this slenderness ratio and calculate phi C FCR, and then based on this phi C FCR calculate area required equal to PU over phi C FCR. So from here we will get some value of area, and it will be equal to B into T. And here we can assume the value of B or T, or otherwise we can go for the next, B over T should be less than 10.8 millimeter. So we can write B in the form of T and we can substitute over here to find the value of T, or we can write this expression in terms of T and then substitute the value of T over here to calculate the B value. So by using these two expressions we can calculate the B value, or we can also use the third expression, B should be greater than 3D. So from here we can calculate the B and then substitute this B value over here to calculate the T, and then satisfy this third condition. So in this manner we can select the B over T value, and after selecting the B and T value we can again check all the four criteria. Means slenderness ratio should be less than 140, we can check this. Then based on the actual slenderness ratio we can calculate phi C FCR and we can calculate phi C PN, and it should be more than FU. Then we can check B over T ratio and B should be greater than 3D. So we can satisfy all these criteria just like the design of compression member. Okay, after deciding the dimensions of lacing element, so next is the design of N-type plates, because in case of built-up section we have ties at the end. For example, it is a channel section like this, so we have tie plates at the ends. So if this is S, then this dimension will be equal to S, and the thickness of this plate will be S over 50. So thickness of plate, the N-type plate should be S over 50. S is 378, so it will become 7.56. So we can use 8 millimeter thick plate, or we can use equal to the lacing plate, so we can also go for the 10 millimeter plate. Okay, then the length of the tie plate equal to S, it should be equal to S 378 millimeter, mean the length will be this one S, and width of the end plate will be equal to the width of the section. So the width of the section is equal to 250, mean gap between the channels, plus 2 times the flange width of the channel. So it will be 474 millimeters. So our end tie plate will be 8 millimeter thick, 470 millimeter wide, and 400 millimeter long in this direction. So that's all about the design of compression members. So up till here we have studied about the design of compression members by using hot rolled section. Then we have discussed about the design of built up section, or the design of compression member using built up section. And for built up section we have studied the two cases. In one case we have designed the built up section using tie plates, and in the second case we have designed the built up section by using lacing elements. If you have any question related to the design of compression members or any other topic, so you can comment in the comment box,